Uh, Now let's see question 6. Now let's move to question 6, which addresses two critical challenges in machine learning: overfitting and underfitting. Let's look at overfitting and underfitting. Overfitting occurs when a model becomes too complex and essentially memorizes the training data, including its noise and peculiarities. An unfit and overfit model achieves very high accuracy on training data but performs poorly on test data. It has learned specific noise patterns rather than the underlying true relationship. Underlifting is the opposite problem. The model is too simple to capture the underlying patterns in the data. Both training and test performance are poor because the model hasn't learned the real relationships. The model makes overly simplistic assumptions and misses important patterns. How to detect and prevent? How to detect these problems? Overfitting is shows itself as a large gap between training error and test error. Training error is very low, but test error is much higher. Underfitting shows consistently high errors on both training and test data. The model is just not good enough. To prevent overfitting, we use several strategies, regularization techniques like L1 and L2 penalties at a cost to complex models, discouraging them from becoming too intricate. Cross validation helps detect overfitting early. Early stopping halts training before the model overfits. Feature selection removes irrelevant features that contribute nothing but noise. Collecting more diverse training data helps with more examples. The model is less likely to memorize. Ensemble methods combine multiple models, which often generalizes better than single models. Let's see bias variance perspective. Let me explain this from the variance perspective. This provides another way to understand these problems. Bias refers to errors from making overly simplistic assumptions. High bias means that model makes very wrong assumptions and misses important patterns. This is underfitting. The model consistently makes the same types of mistakes. Variance refers to errors from being overly sensitive to training data fluctuations and noise. High variance means the model learns noise along with true patterns. This is overfitting. The model makes inconsistent predictions on new data. The optimal model has low bias plus low variance, giving us the best generalization to new data. Simple models like linear regression have high bias and low variance. They are consistent but often wrong. Complex models like decision trees have low bias and high variance. They fit training data in perfectly but don't generalize well. We all need to find the sweet spot for the to balance both. Let's see the summary of this video. To summarize part 3, dimensionality reduction reduces complexity and improves generalization by removing noise and redundancy. Feature extraction creates new feature by transforming existing ones. Discovering hidden patterns. Feature selection removes irrelevant features while keeping original features intact. Overfitting happens when modules are too complex and memorize training data. Underfitting happens when modules are too simple and miss important patterns. We prevent these problems through regularization, cross-validation, early stopping, feature selection, more data, and ensemble methods. The bias varies trade-off shows that we need to balance model simplicity with expressiveness. Understanding these concepts is essential for building models that generalize well to a real-world data. The conclusion for part 3 of the data science assignment: now understand dimensionality reduction and its importance, the difference between feature extraction and selection, and how to identify and prevent overfitting and underfitting. These are critical skills for building robust machine learning models. Thank you for watching the video. I'll see you in the fourth part with question 7th and 8th. So stay tuned.